What can I do with a lovely triangular chunk of glass? And of course, we'll shine light through it and get a lovely rainbow coming out. It's very important that the sides not be parallel to one another. And what we have is light coming up to this interface. Here is a normal, and the light does not continue to go straight. Does not continue to go straight as it enters the new medium, but it bends away from the normal because it's entering a medium of higher impedance, a slower medium. And then as the light leaves, here is a normal, and the light bends away from the normal. Lovely, lovely. That we get these colors coming out of the chunk of glass. And the conclusion that Isaac Newton reached was that that must mean that we are putting colors into the glass. That indeed white light is composed of all of these colors, and Newton was even able to find a way to get the colors to go together and recompose the white. This would seem like an obvious conclusion to us, but it was very upsetting at the time because everybody wanted white to be pure. And the thought of white being composed of this melange of colors was very upsetting to philosophers and theologians. And it's remarkable that for all of the history of making colors by shining light through chunks of glass, it wasn't until Isaac Newton that this conclusion that the colors are, that the white is made up of colors came. But that is what we believe today. And I expect you to know how these... Wait a minute. How can it be that these colors are not all bending the same amount? That the bending has to do with the change in velocity. And upon what does the velocity of a wave depend? And the people respond, it depends solely upon the medium. For a non-dispersive medium. But it turns out that this spreading of the colors apart is exactly what we mean by dispersion, and that glass is a dispersive medium, and so the velocity of the waves depends upon the medium and upon the frequency or wavelength. That what we see is the red was bent towards the normal, and so was the violet, but the violet was bent more towards the normal than the red, and upon leaving, the red was bent away from the normal, and so was the violet, but the violet was bent more. And that is because violet goes faster than red in both glass and in air. That all frequencies do not travel at the same speed, that they travel at varying speeds, and the fastest, the most energetic, and hence the most bent is violet, and the slowest, the least energetic, and hence the least bent is red. I expect you to know this ordering, that the colors, and that is the ordering from least to most bent. Do not think of it as the ordering from top to bottom, or surely on the test Mr. Houghton will give you this prism to talk about, in which case from top to bottom it's Vib G Yor, it's not Roy G Biv, but it is still the case that least bent is red and most bent is violet. So glass is a dispersive medium. Water, of course, because we have rainbows, water is a dispersive medium. It turns out that air is a dispersive medium for light. Indeed, the only non-dispersive medium for light is a vacuum. That all colors from violet through red would travel at the same speed through a vacuum. Indeed, so would all the rest of the electromagnetic spectrum. That radio waves, microwaves, infrared, all the colors, ultraviolet, X-ray, gamma, all of them travel at the same speed through a vacuum. But through a dispersive medium, which is everything other than a vacuum, it is the higher the frequency, the faster it goes. Can you think of an example of course, we just spoiled that, didn't we? The rainbow. And I want to go through the mechanics of the rainbow in some detail. That you have to have the sun behind you, and then you have water droplets that the sunlight is entering. And as the sunlight enters these water droplets, it is refracted. There's the normal, gets bent towards the normal, but it is dispersed. The violet is bent more towards the normal than the red. But then, and this is why you have to have the sun behind you, there has to be this total internal reflection that occurs. That the angle of reflection would equal the angle of incidence, but then as it leaves the raindrop, the red is going to be bent less than the violet is. And this red comes down into this person's eyes. Here, the same phenomenon goes on, except this time it would be the violet light which would enter the person's eyes. Here in the middle would be an angle of 42 degrees, and at that angle is where you would see the rainbow, and so 42 everywhere, hence the arc, with violet at the bottom and red at the top. But wait a minute, there's another rainbow. What about it? Indeed, that is a very interesting phenomenon, and it has to do with total internal reflection happening twice within the raindrop, and so they don't come out, enter at the top and leave at the bottom, but they enter at the bottom and leave at the top. And again with here, let's come up here, the violet being dispersed, bent more on both entering and leaving the raindrop, and so the violet would be, this is at another angle, this is at 52 degrees, and the violet would be at the top and the red at the bottom, as you can see here. Remember that your eyes are less sensitive to violet than they are to other colors, and so we have a very hard time seeing the violet part here. That's because all of these are probably equally intense and your eye can't pick up violet so well. I can see the violet better. No, that's just a strong red, isn't it? The violet's out here. I expect you to know all of that. Okay, back to your perception of color in your eye. And on the retina of your eye, there are two different kinds of nerves. One are called rods because they're rod-shaped, and they just distinguish between light and the absence of light. We call that black and white vision. And the other are called cones, and they can distinguish. They have pigment, and they can distinguish between the different parts. There are 3 different kinds of cones, which we will call the violet, green, and red, although sometimes I will call them the blue cone, but I would prefer to say violet to distinguish between what we would call a pretty blue and where this cone goes through its peak. So you have these 3 cones in your eye, and one of them has a resonance in the violet part of the spectrum, and the other resonates in the green part, and the last one resonates towards the red part of the spectrum. Hence their names. But please note that they all fire throughout the whole spectrum. It's a little bit more complicated than I would like to indicate, but that's something I got off the internet. Here's the picture I'm going to go with. And so for any color that goes into your eye, all of them are sending messages back to your brain. And the key is that your brain is sorting out the relative intensities. If all of them are firing at their maximum rate, then of course your brain sees white. But if these 2, the green and the violet, are firing at a high rate, but the red is firing less, which could be right here, green and violet firing equally, red firing less, that is when your brain sees cyan. Green firing strongly, red and violet firing less, then your brain sees green. Red and green firing equally, violet firing less, your brain sees yellow. And the red firing strongly, and the green and the violet firing weakly, that's when you see red, and so on over here. So there you know the formula for what goes on in your brain for white plus these 5 colors. I want you to know 8. Black. What sort of firing would these cones have for you to see black? Indeed, none of them firing would be black. So that's up to 6. 5, 6, 7. That's up to 7. And the last one is one that does not appear in this picture, and it does not appear in the rainbow. That's very important. This would be if you had equal firing of the violet and red and weak green. In the rainbow, where you get equal firing of the violet and red, you get strong green. So to get weak green at that point would have to be done artificially. It has to be done polychromatically. You would have to artificially create violet light and create red light and not make green light. And if you put those together, you get the last color, and that's this color here, which we call magenta. So the violet is not very obvious to me here. Cyan, green, yellow, red, and magenta, which does not occur in the rainbow. That's very important. Hold on to that. I've already used these terms, but let us consider this yellow here. Looks just like that in the rainbow too. But you can make that yellow by sending in a single frequency that's right here. And that will look yellow. But you can also make yellow by sending in green and red light. That would be made of 2 frequencies. We call that polychromatic. You could also make yellow by sending in the whole spectrum here. All of these colors, or some of these colors. But if you send in light in this part, many different wavelengths, it will look yellow. And your brain cannot distinguish the yellow of the rainbow, which is a single frequency, monochromatic, from a yellow that is made with many. As long as you make your brain respond so that it gets equal firing of the green and the red cones and weak violet cone firing, your brain calls it yellow and cannot tell the difference at all. The only way to tell would be to send it through a prism, and if it was monochromatic, there would be a single path in and out of the prism. And if it was polychromatic, it would disperse into however many wavelengths made it up. Sometimes we have a cone that doesn't work as well. Either that pigment is missing from the retina, or its signals to the brain get messed up. And then you have what we call color blindness. Here is a picture of here's an image for a normal sighted person, and here would be an image if the red cone was not working. We call that red-green color blindness. You can't tell the difference between red and green. And that would be because you are missing the red cone. You can tell the difference between green and violets, that the blues and the greens look different. The yellow looks different. That's because of a different mixture of the green and the violet than you get over here. Doesn't look like that. Let's see what it looks like here. Yellow. Yeah, that when we're up here in the green, we've got some violet content, and here we're not getting any violet content at all. And so you can tell the difference between yellow and green, even if you're missing the red cone. Most animals seem to be missing, dogs, cats, lions can see yellows and blues and violets and greens, but they cannot distinguish between green and red. And so you have the deer, which if you dress in blaze orange, the deer can't tell you apart from the green of the forest or the brown of the trees. Owls are the only bird which have no cones at all, and that they only have black and white vision, but very good black and white vision. All the other birds, as you can tell from the fact that they color themselves so that other birds can see them and say, "Hey, you look sexy." All the other birds do have full color vision. And then you have some things like butterflies and bees, and I'll let you tell me in class what bees can do that other animals can't. Now we're moving on from light, which is energy. And if you add light to light, then you have both of their energies. So if you had red light and then you added green light to it, you would have both the red and the green, and it would look yellow. And then if you added violet light onto the red and the green, then you would have all three of their energies. It would look white. It would excite those three cones in the brain. But pigment is different. This is like a blob of cyan paint, and pigment does not have energy. If you take this cyan into a pitch dark room, it looks black. It does not have the property of being cyan. What it has the property of is of taking away the chemicals which make up this pigment, absorb. Let's see, I want it to look cyan. What do I want to have reflect off? And the people say you want green and violet to reflect off. That is, I want this pigment to take away red. Let me move that up to the front. And something about the chemicals and the bonds in here resonates with the long wavelengths of red, and it takes it away. So the only thing reflecting off are the violet and the green, and so it looks cyan. If you take some yellow, what is it going to take away? Well, what do you want to have reflect off of this paint in order for it to look yellow? And the people say, I want red and green to reflect off. That is, I want to take away, I'm not going to get that back, I'm going to take away the violet. And so, if you mix yellow pigment, which has a chemical which resonates with the short wavelengths of violet, with cyan pigment, which has a chemical which resonates with the long wavelengths, then both of those absorbing chemicals will be present, and so they will take away both the violet and the red, and the color that you're going to get here is going to be green. Mix yellow and cyan and you get green. Not so dramatic here, but I'm sure you've had the opportunity in your life. Finally, I would like you to do this problem. This is cyan light magenta light, and you need to think about, could magenta light be monochromatic? No. What wavelengths would make up magenta light? What wavelengths does cyan pigment take away? And so what color would this cyan look like under magenta light? Thank you.